I welcome the students of Physics 6th semester for the second session of the online classroom session. So, in this session, we shall discuss the rotational spectroscopy. For rigid rotors and harmonic oscillators, displacement of atoms on either side of the center of mass. The rigid rotor is nothing but the bond which is connect between two atoms of a diatomic molecule is a rigid one, so which rotates about a fixed axis is called as a rigid rotator. The molecular rotations and rotational spectra and vibrational spectra is represented by this figure. The potential curve representing the ground electronic state, and which consists of a number of vibrational levels, and the each vibrational level consists of different rotational transitions which are also shown in the figure. Hence, there are transitions for rotational motion and a transition for vibrational motion of the atoms of the molecule, which corresponds to lines. So hence the molecular spectra is a band spectra. So we shall discuss the pure rotational spectra of a diatomic molecule, which is the most simpler case. Instead of taking a polyatomic molecules, we shall discuss with a diatomic molecule, which simplifies the energy of a diatomic molecule due to rotation. The basic concept of this rotational energy of a molecule, so which is quantized. The equation E is equal to h nu, where A is the energy in joules, h is Planck's constant in joule second, and nu is the rotational frequency in hertz. The range of rotational frequencies is about 8 into 10 raised to 10 to 4 into 10 raised to 11 hertz. The wavelength corresponds to this frequency, that is lambda, is nearly equal to 0.75 to 3.75 millimeter. So these wavelengths fall in the microwave region of the electromagnetic spectrum. Hence, the rotational spectra observed in the microwave region of the electromagnetic spectrum. A diatomic molecule can rotate around a vertical axis as shown in the figure. In this, the rotational energy is quantized, and this type of motion that we call it as rigid rotor. So let us consider a diatomic molecule in which two atoms held together with a massless rigid rod. So that model we call it as a rigid rotor. In a diatomic molecule with the different atoms of mass m1 and m2 are considered, whose distance from the center of mass are r1 and r2 respectively, as shown in the figure. The moment of inertia of this diatomic molecule about the given axis passing through the center of mass is given by, that is, I is equal to m1 r1 square plus m2 r2 square. The two independent rotations of these molecules are with respect to the two axes which are passing through the center of mass C and are perpendicular to the bond length R. The rotation with respect to the bond axis is possible only for classical objects with large masses. The center of mass is defined by equating the moments on both the segments of the molecular axis. M1 R1, that is moment of the first mass about the center of mass, so that is equal to M2 R2, the moment of the second atom about the center of mass. The moment of inertia is given by the equation, that is I is equal to M1 R1 square plus M2 R2 square. On simplification of these two equations, finally we will arrive the moment of inertia of the diatom molecule in terms of reduced mass of the system. Hence, that from equation number 5, it is observed that the moment of inertia of the diatom molecule is given by the expression that is mu into r square, where mu is called as the reduced mass of the system, and that is equal to m1 m2 divided by m1 plus m2. So, and also it is represented by equation number 6, that is 1 over mu, that is equal to 1 over m1 plus 1 over m2. The rotational levels of this rigid rotator of a diatomic molecule are obtained using Schrodinger wave equation. In the harmonic oscillator model, the energy was all potential energy. In the rigid rotor, it's all rotational kinetic energy. By solving the Schrodinger equation for rotational motion, the rotational energy level is given by, that is ER, that is equal to I into omega square divided by 2. So that is the rotational kinetic energy is given by 1 by 2 I omega square, and that is also given by in terms of angular momentum, that is L square upon 2 pi, where L is called as angular momentum, that is equal to I omega. So L square leads to h upon 2 pi whole raised to square j into j plus 1, where j is called as rotational quantum number and takes the value 0, 1, 2, 3 and so on. Therefore, for a given rotational quantum number, the energy of a rotational spectra is given by E j, that is equal to 1 over 2I into bracket h upon 2 pi whole raised to square into j into bracket j plus 1, and it is also given by the expression h into c into b into j plus 1, which is given in the equation number 7, where b is called as the rotational constant. In equation number 7, the energy of a molecule, the rotational energy of a molecule is solely depends upon the rotational quantum number and the value of B, that is rotational constant, wherein the rotational constant solely depends upon the moment of inertia, since H, C are constant in the rotational constant equation. Hence, from this rotational constant, once we know the rotational constant, we can easily calculate the moment of inertia. Once the moment of inertia of the molecule is known, we can also calculate the internuclear distances of the molecule, that is the distance between the two atoms of a molecule, that is R, that can be calculated with the help of this rotational spectra. The energy difference between the two rotational levels is usually expressed in centimeter raised to minus 1. The wave number corresponding to the given energy difference is given by, that is nu is equal to delta E upon hc. The rotational energy is quantized as Ej, that is equal to s square upon 8 pi square I into j plus 1, that is in terms of joules. Therefore, Ej is also given by, that is equal to B into j plus 1, where B is called as the rotational constant. Hence, for the different values of rotational constant, we have a different energy levels which are given in the figure. For the value of j, that is equal to 0, the rotational energy, that is equal to 0 times B, j equal to 1, that is 2 times B, j equal to 2, that is 6 times B, and so on. For j is equal to 6, it is 42 times the rotational constant. That means from the picture it is observed that these rotational energy levels are not equally spaced. So that means energy difference between any two levels is not same. So the specific rule, that is selection rule for this rotational spectrum, that is j is equal to plus or minus 1. Hence, for delta j, that is equal to plus or minus 1, delta J that corresponds to plus 1, that corresponds to absorption spectra. If delta J that is equal to minus 1, that corresponds to emission spectra. So the transition from different energy levels of rotational spectra are shown in this figure. So in the next class, we shall start with this vibrational spectra of a diatomic molecule.